Hi, this is Gary Rubenstein. This is the second part of a video of how Archimedes found that the volume of a sphere is 4 pi r squared. And as a refresher from last tutorial, he created a regular polygon with an even number of sides. In this picture there's 10 sides. And if you rotate this around line AF, you see what happens is that you get a figure that looks kind of like a sphere. I'll just rotate it halfway around. And when I look at this thing is composed of 3 frustums and 2 cones. And using the formulas for the volume of a frustum and the volume of a cone, he's going to find the complete surface area of this figure and then show that if the sides, number of sides is a lot more, how that approaches 4 pi r squared. Here's a two-dimensional picture. For this one I have an octagon inscribed, regular octagon inscribed inside a circle. And I've drawn in the most important points are labeled. AC is the sort of diameter of the circle, and B is a point there on the octagon. And I'm going to label some of the lengths in here. Okay, so what I have here, I drew in a couple of lines. I drew these vertical lines to connect these vertices. I also have line AB drawn in and a bunch of diagonals drawn in also. A couple of observations. One is that since it's a regular polygon, all of these lengths, all of these sides have the same length, which I'm calling S. Also, there's a lot of triangles in this picture, and all of the right triangles in this picture are similar. And it's not completely obvious that that's true, but they all have right angles in them. And for instance, this angle here is a 22.5 degree angle because it's half this 45 degree arc. So this triangle is going to be similar to, for instance, this triangle, because this angle here is also across from this arc. And all these triangles that sort of have as their all of these right triangles that have their corners here on this diameter are all similar. They all have the same right angle, and they all have this 22.5 degree angle because it's half of the 45 degree angle of the intercepted arc. That's actually true for this big triangle here also. Triangle ABC is also similar to the others because this is a right angle. So we have a lot of similar triangles. We also have some congruent triangles also, but I'm going to now show you how Archimedes derives this formula. First, just a refresher from before is that the volume, the surface area of a cone is pi RL, where R is the radius of the base and L is the slant height. And the surface area of a frustum, that's pi capital R plus little RL. I'll call this S instead of L, where S is sort of the slant height of the frustum, and the R and the big R and little r are the larger and smaller radius of the larger and smaller bases. So the surface area of this figure, after it's rotated around AC, it becomes 2 cones and 2 frustums. This side here ends up becoming part of the cone, whereas these 2 sides ends up becoming the frustum. So the surface area, well, the surface area of a cone is pi r L, so it's pi, I'm calling this R1, R2, and R3. So it becomes pi R1S, whoops. Now the frustum, this first frustum, using the frustum formula, is pi R1 plus big little r plus big R is going to be parentheses R1 plus R2S plus the next frustum is pi R2 plus R3S, and the last the cone that comes out on the right is pi times R3. Yes. And when you combine like terms, you end up with the surface area of this is pi, also factor out the S, pi sorry, 2 pi s times r1 plus r2 plus r3. Notice how there's an r1 here, and there's an r2 here. So there's sort of 2 of each. So we've got this formula for the surface area of this sort of three-dimensional shape that comes up. But this isn't really that useful because we have this r1 plus r2 plus r3. I want to show you how we can relate that to other parts of this circle. Now, because of similar triangles, we can say that r1 over a1, a1 is from here to here, is equal to r2 over a2, which is equal to r3 over a3. These things are the long side and the short side of each of these similar triangles. And the big similar triangle ABC has that true also. Well, AB is the sort of medium length leg, or the bigger leg, whereas the smaller leg in that case is BC, which is equal to S. Now, if you do some cross multiplying, if I were to cross multiply this with this, I would get that R1S equals A1 times AB. If I cross multiply this one with that last one, I would get R2S equals A2AB. And if I do the last one, I would get R3S equals A3 times AB. Now if I add these three equations together, I would get R1S plus R2S plus R3S equals A1 times side AB plus A2 times side AB plus A3 times side AB. If I divide at both sides by S, I get R1 plus R2 plus R3 equals AB, can factor out the AB there, times A1 plus A2 plus A3 all over S. But A1 plus A2 plus A3, take a look, there's two A1s, two A2s, and two A3s that make up the entire diameter. So A1 plus A2 plus A3 can be replaced with half AC over S. Now we can take this equation up here and replace the R1 plus R2 plus R3 with this expression. So we have the surface area is 2 pi S times AB times 1/2 AC over S. Now I'm going to simplify this a bit because the S's can cancel out and the 2's can cancel out. And I'm going to replace AC with 2R because this time the R, this is a new R, this is the actual radius of the original circle. So now I have pi times AB times 2R. Now AB, if you look up here at AB, as the number of sides gets bigger and bigger, AB is going to be really close to AC, which is 2R also. So this is going to, I'm going to just write arrow, it's going to go to, as the number of sides goes to infinity, pi times 2R times 2R, which is your famous 4 pi r squared. So this is what happens as the sides, I'll call them n sides, as n goes to infinity. And there you have our famous formula for pi r squared. Just to finish up, here it is with the 10 sides again and all the auxiliary lines drawn in. So as this is moved with 10 sides, we end up with some frustums and some cones. And that is what Archimedes found, the surface area of where the limiting case, as this thing goes to infinity, this thing would be, for all, this would be approximately, or becomes a sphere for the infinite case. So I hope you like that proof. I think it's one of the Archimedes' best proofs, so I hope you like that. Thank you.